In previous lecture, we studied for the Fermi surface, and Fermi surface is very informative to understand solid-state materials. And this lecture will deal with the Fermi surface on the high magnetic field. And we know that the Hall effect is that if the sample is in here and the electric current flows from this side to this side, it is electric current density direction. Then when you apply magnetic field in this region, and because there is Lorentz force QV cross B, and also here when we define that V cross B case, and this charge plus charge can be accumulated in the upside, and the image charge can make in the opposite side, and therefore the internal electric field can be like this, and we call it is a Hall electric field. It is a Hall effect. But how about by increasing, how about the increase of magnetic field much higher and higher, then the electronic trajectory can be the radius decreases more and more, and at some critical points for high magnetic field, the deflection region can be more decreases, and the radius of circulation decreases, and so that in some cases, and the motion the motion of the electron under high magnetic field can have this closed loop. Then we call it as a Landau level, and then when we think that in this case, and it is localized and by circular motion in the materials. Therefore, in the case, the Landau level generates the quantization of electrical resistance as like insulating state, and because of the localization of the charge carriers. Here we'll in this lecture, I will describe what causes Landau level and the physical origin of this Landau level in more detail. And here, by applying magnetic field in G direction, then 0, 0, B in G direction, and the Maxwell equation says that the divergence B equal to 0, and also curl E plus 1 of C partial B partial T equal to 0. Because the divergence B equal to 0, we can define that there is a vector potential, and the vector potential is that curl A. And curl means that the rotation of some electromagnetic field, but the divergence means that the diverging direction, and the rotation of field. For example, when we see that the magnet and the NS, and there is a magnetic field rotates like this, and the rotation of magnetic field and rotation of magnetic field case, and that there is no divergent composition, divergent component. It is the origin of that curl of divergence equal to 0. Then we define that vector potential. Here is A is the vector potential. Then if we insert to this Maxwell equation and curl E plus 1 over C partial T curl A, then we can define that curl E plus 1 over C partial A partial T equal to 0. And here you can, from this any gradient of curl equal to 0, then we can define that the scalar potential phi such that the curl of gradient phi equal to 0. And gradient means that in some equipotential or a field line, and gradient is that directional and perpendicular direction of the field, and therefore the gradient of curl equal to 0. There is no contribution of the curl in the gradient, and therefore we can define that it is a gradient. Therefore electric field plus 1 over c partial A partial t can be write down minus gradient phi. It is a scalar potential and the A is a vector potential. Scalar potential is component of the gradient, and the vector potential is component of the curl. And here electric field therefore can be written down like a scalar potential and also vector potential. Then in this case let's consider for the electrodynamics of electrodynamics. But here basically electrons are waves in quantum mechanics, but in classical point of view, electrons can be classified by the classical particles. And here we use that the classical mechanics and not dealing with quantum mechanics. At first, when we describe the electrons as a classical mechanics, later it can be extended to the quantum mechanical description. And here in classical mechanics, in the Lagrange equation, in classical mechanics is that ddt Lagrangian derivative with velocity minus Lagrangian with position equal to 0. And here Lagrangian means that the kinetic energy minus potential energy. And the force F equal to ma. Ma means that x2 dot. X2 dot is that it is a Lorentz force. It is a Lorentz force, and the force is the time derivative of momentum. In this case, the momentum is that the generalized momentum is the Lagrangian derivative with velocity. It is generalized momentum. Then it is a generalized momentum, and also therefore it is a force from the Lagrange equation. And it is like that partial L partial xi. Then here, because electric field we already calculated in the above, and E minus E gradient phi minus E of C partial A partial T, and also plus E of C V cross B equal to curl A. And here, let's calculate this term and this term. This term is 1, this term is 2. And the first term is that V cross curl A is that from the Beckham rule, gradient V dot A minus V dot gradient A. It is Beckham rule. The second one is that let's consider ddta. It is a position vector and time function. Then here, because we can think about that partial differentiation. Partial differentiation of the A and x t, and also here in the vector. Because here vector x and t derivative, and here because let's say that it is xj, because it is a time derivative and partial xj over partial t should be concluded, and it is a j component. It is a vector representation. Then it is that partial a partial t plus here it is a v, and also it is gradient. Therefore, it can be write down the v dot gradient and a x t. Because the first one and the second one and it is a plus and minus. Therefore, when we summate here, this can be subtracted with each other. Therefore, the force can be write down as minus E gradient phi plus 1 over C. And then the first one is that here partial A partial T dA dt minus gradient V dot A, yeah, from this one. Here it is force is a negative potential energy. Therefore, in this case, let the not dynamic but the static magnetic field. In the static magnetic field, dA dt equal to 0 in static magnetic field. And therefore, in this case, in the potential energy can be write down E phi minus E over C V dot A. It is a potential energy. The Lagrangian is that Lagrangian is a function of velocity and position and time. Then it is x what have mx dot square minus potential energy minus E phi plus E over C x dot A x t. The canonical momentum is that Lagrangian. Here, let's say that is a component Lagrangian and partial xi dot. Here, xi means that vector component. Then it is that m xi dot plus E over C A. Here is the vector component AI. And therefore, the mv equal to momentum minus E over C AI. Here, when you make the vector representation can be omitted. And this Hamiltonian is that momentum. Hamiltonian is a momentum and qi and pi function. Therefore, it is that 1 over 2m, and it is a canonical momentum. Pi minus E over C AI square. It is a canonical momentum. Therefore, on the magnetic field, this Hamiltonian can be like this. And also, let's calculate the electron's trajectory on the magnetic field. And here, mv dot is that E over C V cross B on the magnetic field. Then E over C ijk, and vx, vy, vg, and also jj00b. Then eb over c in the I component, vy minus j component vx. Then here, let's for mathematical calculation. For simple method is that we define that in xy plane, in the x direction is the real value, and the y direction is the imaginary vy. Then we can define that the vector can be considered as a complex plane. And here in the complex plane representation, and vx dot plus I vy dot, it is a velocity, then it is that the eb over mc, and the x component is that the real value vy, and the y component is imaginary value, imaginary minus I vx. Yes, I is not a vector basis. It's not a vector basis, but imaginary. Then it is that minus I eb over mc vx plus I vy. Then here we can define that cyclotron frequency. Cyclotron frequency is that eb over mc, and also let that v bar is that the vx plus I vy. Then the above equation can be like this: v bar dot is that I omega c v bar. Then it can be we can be calculated by the separation of variable dv bar dt equal to I omega c v bar. Therefore, dv bar dv bar v bar equal to I omega c dt. When we integrate in both sides, then the ln v bar equal to I omega c t plus constant. Therefore, v bar can be write down v0 bar exponential I omega c t, but here let's include the phase factor phi. And from the definition, from simple calculation, we can know that v0 bar can be write down vx squared plus vy squared, because the v bar 0 here, v bar can be defined like this. And also in the real space, from this above definition, in the vx can be write down v0 bar cosine omega ct plus phi, and the vy is that v0 bar sine omega ct plus phi. And vg equal to vg0, it is constant value. Then it can be write down also in the x equal to x0 plus integrate in with time, and v0 bar over omega c sine omega ct plus phi, and y equal to y0 minus v0 bar over omega c cosine omega ct plus phi, and the g equal to g0 plus vg0 t. It means that it is a circular helix motion on the magnetic field in the g direction, and then the circular motion in the xy and g direction goes up, and it is a helix, circular helix motion. Yeah, it is a classical description of electron trajectory on the high magnetic field. But we should calculate this classical classical point of view by quantum mechanical description, and here we will calculate by quantum mechanical description. Let me say that it is a Landau level. The first one is classical. Anyway, then it is classical. Classical trajectory. And the second one is the quantum mechanical. Then the quantum mechanical description is that the important thing is the commutation relation. And on the magnetic field equal to 0, 0b, then the vector potential A is that 1/2 B cross X. And here it means that 1/2 IJK and 0, 0B and XYG. Then it is that 1/2 I minus by and j equal to is bx. Therefore, the it is a vector potential A can be write down minus 1/2 by and 1/2 bx and 0. Then it can be proved like this. Because of the magnetic field and the vector potential has this kind of this behavior, then let's calculate by the call A I component. Then epsilon I jk partial xj ak, but here ak vector here magnetic field. But let's say that the magnetic vector potential is that 1/2 B cross X in K component. Then epsilon ijk 1/2 epsilon ijk partial xj and the epsilon klm. Then BLXM. Then it is that 1/2 epsilon ijk epsilon lmk BL partial xm partial xj. Then this one is the Kronecker delta mj. And also from the rainbow rule, it is that 1/2 BL can be BL Kronecker delta mj and Kronecker delta IL Kronecker delta JM minus Kronecker delta IM Kronecker delta JL. Then it can be right because M should be J. In the M should be J, then because of a three-dimensional space and summation is excluded, summation is omitted. Therefore, it is 1/2 BL. It is 3 Kronecker delta IL and minus here m can be j, and the j equal to should be L, therefore IL, delta IL. Then in this case it is a 2. 3 minus 1, 2 cancel with each other, it is a BI. Therefore we can prove that the under magnetic field, then the vector potential is like this, and we can prove. Then from like this anyway, and from the mxi dot is that canonical momentum is the pi minus E of cai, and we can write down, and the Vx is that 1 over m, and px here vector potential, vector in the x component is that the vector potential, it is 1/2 by minus 1/2 by, therefore plus EB over 2C y. Okay, from the vector potential component, and y component of vector potential is 1/2 bx, therefore Vy is that 1/2 m py minus EB over 2C x, and Vg is that Pg over m. It is V can be write down like this. And from the in quantum mechanics we know that xp xi pi pj is that the chronic delta ij and also ih bar, and it is a quantum mechanical commutation relation. It is very important because it is due to the Heisenberg uncertainty principle. And also therefore by using this relation, let's calculate the Vx commutation relation Vy. Then it is that the 1/2 m square, and also px plus EB over 2cy and py minus EB in 2cx. We know that the P and Pij, and also Xi, Xj, it is a commutation relation equal to 0. It is commutable, and it is exactly defined, but X and P cannot exactly define. And by using this commutation relation, and also here 1 over m square, and here minus EB over 2C, and px and x, and plus EB over 2C, and y and py. Because of this commutation relation and 1 over m square, and the first one is that the minus IH bar, and second one is IH bar, and therefore there is 2 here, m square c IEH bar b, and like this, and the Vx and Vg and the Vy and Vg equal to 0, because in the px and pg and the py pg is not commutable, is commutable, therefore it is equal to 0. Therefore, and we can define that operator Q as that normalization factor m square c over E B H bar Vy, and P is that m square c over E B H bar Vx. Let's define that this operator. Then basically in this case, in the P Vg and also Q Vg equal to 0. And also P and Q, Q and P, Q and P equal to I. Therefore, the Hamiltonian is that 1/2 m Vx square plus Vy square plus Vg square. Then it is that Vx, Vy, like that, the amplitude here, and 1/2 and it can be, you can simply calculate, and the result is that the Vx and Vy is like the square root, can be E be h bar over m square c, and q square plus p square, and Vg square is not Vg square. Then here, this term is that it is the perpendicular direction of the magnetic field. This is parallel direction along the magnetic field. And this solution, when you see this one, this solution is the harmonic oscillator. Yeah, because when we define that creation and the annihilation operator, and here A is the operator 1/2 in the Q plus IP, and the A dagger is that 1 square root, 1 over square root, and Q minus IP. Then the commutation relation A and A dagger is that 1/2 Q plus IP and Q minus IP. Then 1/2 minus I Q and P plus I P and Q. Then it is that Q and P equal to I. Therefore, it is 1/2 1 plus 1 equal to 1. And also A and A and A dagger A dagger equal to 0. Then let's consider A dagger A is that 1/2 Q minus IP and Q plus IP. Then it is a 1/2 Q square plus P square, and it is commutable A dagger. Then, and the Q square plus P square is that A dagger A plus A dagger. Therefore, it is that A dagger plus 2A dagger A. Then it is 2A dagger A plus 1. Therefore, the harmonic oscillator term H perpendicular direction is h bar omega c, and also p square and q square is that A dagger A plus 1/2. Therefore, the energy in the perpendicular direction in the xy direction, h bar omega c and n plus 1/2. It is a quantum mechanical description. Therefore, in the energy is that h bar omega c and n plus 1/2 plus h bar square k g square over 2m. We call it is the Landau quantization. We call it as a Landau level. And also omega c is that the cyclotron frequency EB over MC. And also it is very important, and the physical meaning of this Landau level is very important. Yeah. Okay. Then here it is just calculation of Landau level. In the next preceding lecture, we'll describe the physical importance and the physical interpretation of Landau level.